Okay, so last time we were talking about triple integrals, so just a quick reminder, when you're thinking about triple integrals, you have to think about triple integrals from the point of view of, I'm going to loosely speaking say the mass application, right? We've had mass applications for double integrals. We had a mass application for single variable integrals. This point of view has some advantages, some disadvantages. The disadvantage is obvious. It's not as sort of dimensionally opulent as looking at, for example, a single variable integral as area under a graph. You can see the integrand geometrically. There's satisfaction in that. Right? Likewise, dimensionally opulent. We can think of double integrals as representing volume under a graph surface. And again, it's nice to be able to see geometrically what the integrand looks like, and you can visualize what the integral is computing from that point of view. And so that, again, luxurious, right? Very nice. But we cannot afford this dimensional opulence going further, right? So we're thinking about triple integrals. Can't do it. Right? So this whole point of view, this kind of the graph point of view, the geometric point of view on integrals, I find myself more often than not pulling students away from it. It's not that it's bad, it's not that it's wrong. It's fine, it's good in many ways, right? But students tend to rely on it exclusively, or at a minimum to make this the cornerstone of their point of view on integrals. And I think that's a mistake. Right. So just a reminder, I won't go do the whole spiel like we did last time, but just a reminder, this is to be sort of de-emphasized, not discouraged, right, but de-emphasized. And certainly going forward, certainly thinking about triple integrals, think about triple integrals from the point of view of this mass application. And as such, it makes it easier to do that if you think about double integrals from the point of view of mass applications, and likewise single variable integrals. Okay, all right, so we talked about all that last time. Blah, blah, blah. So now let's talk about how to actually compute these things. So they're going to be computed with iterated integrals, just like double integrals were. That's really good news, right? I mean, this is big news for double integrals. I mean, how to compute double integrals directly from the limit definition seems formidable and intractable, right? But, I mean, these single variable integrals are easy to compute. And then once you've computed the inside one, well, then there's another single variable integral, and that's easy to compute. I say easy. It's familiar, right? It's a pain, of course, right? There's a bunch of different techniques, etc. But we have techniques. It's something we can do. Okay. All right. Why are double integrals able to be computed with iterated integrals? Well, we made a three-dimensional picture to motivate why this works. Right? I said, let's think about each one of these from the point of view of volume. Right? Let's think about that volume under a graph example, and you can relate both of these to that. And that's nice. But so our problem, you can see this coming. If it took a three-dimensional picture to motivate this computation of double integrals, well, hopefully no surprise, it would take a four-dimensional picture for me to motivate why you can do morally the exact same thing for triple integrals. And I can't even begin to draw a four-dimensional picture, so we're not going to try. What I'm going to do is just appeal to your sense of pattern, right? And assert that this can be done. And I'm going to point out what the pattern is. So here's the pattern that is upheld. With double integrals, you look at your domain. The x integral has bounds that come from, well, what's the range of values of x on, of course, that domain. Right? No surprise. And then when you look further to the inside, if you want to know, well, what are the bounds on the y integral, well, the y bounds are going to depend on x. Right? And it's the range of values of y. Now, again, no surprise, it's the range of values of y. But specifically, it's the range of values of y on that x slice, specifically for that value of x. Not on the whole domain. Not on all of D, but just on that x slice of the domain. Okay. All right, so that pattern's going to continue. We have a domain. We'll call it R here. Look what I did. Shame on me. You know what's funny is I just noticed this. I've been using these notes for several years, and no one's ever caught this before, but that's supposed to be an R. Sorry about that. I must have changed my mind as I was writing those notes. Anyway, okay. So we have some domain called R, and we're going to we're going to have an x integral. Let's say on the outside, there are x bounds that are going to be the range of values of x over that domain R. Okay. Now, just like with double integrals then, we're going to then fix a value of x. We're going to look only at that x, wrong color. We're going to look only at that x slice. Color. Green, here we go. Only at that x slice of the domain. Not at the whole domain. We're just going to look at that x slice of the domain. And on that x slice of the domain, we'll talk about, well, what's the range of values of y on that x slice of the domain, again, for that specific arbitrary value of x. So those y bounds, just like in double integrals, those y bounds are going to be functions of x. Okay, we're going to draw the picture in just a moment. Just want to notice the algebraic pattern. So the tricky bit here, right, is that now there's yet another step. There's this z integral on the inside here, right? So what's the range of values of z? Well, the range of values of z, the pattern that we used for determining the range of values of y, continues. The range of values of z, we're going to look at the y slice. Now, don't forget that y slice is a slice of, we've already agreed, an x slice. We're not looking at the whole domain R, right? We're looking at, well, we've previously had decided that we were going to restrain our attention to an x slice of R, and now, because of the y integral, we're looking at a y slice of that x slice of R. And then notice that the values, these bounds for the z integral, they still depend on x. Well, this is all conditional on certain values of x having been chosen, but now they also depend on y. Okay, so I think the color coding there is helpful to see what's going on at what stage in this process. Now let's see what that looks like geometrically. Here's the picture. Okay, so I'm just going to leave the colors as we have it there. We've got this great big solid domain here. There's our domain R. We're going to do a triple integral over this domain. Maybe we're computing the mass inside of this three-dimensional solid. Maybe we're computing the total population of fruit flies inside of this enclosure, whatever it is. We know population density, density of fruit flies per unit volume, something like that, right? Whatever the case may be, why we might be happening to look at a triple integral. Something's accumulating over this solid. We start by looking at the range of values of x. Right? There's a first value of x and there's a last value of x on this solid. That gives me our x bounds. Okay. All right. We then focus our attention on a single value of x. We look at an x cross section. At that single value of x. That's a cross section of our solid at that single value of x. The rest of our attention for the rest of this problem will be only on that x slice of our solid. Right? And now next question, we want to look at the range of values of y. So y is, here's, as I move in the y direction along that slice, that point there is our smallest value of y, and then maybe this point over here is our largest value of y. So y is going to range from some starting value to some ending value on that x slice. Okay. that gives us these y bounds. Okay, lastly, now we're going to fix a value of y. We're going to look at, this gets hard to draw. We're going to look at this y slice of that x slice. Now I appeal to your geometric intuition. That x slice is kind of like this, right? And now I'm taking a slice perpendicular to the y-axis, which therefore is going to be perpendicular to this x slice perpendicular to the x-axis. We're taking a slice of a slice like that, and the slice of the slice is a little segment like that. Right? So it's on that slice of the slice that I want to now know what's the range of values of z. Well, z is going to start at what's the lowest value of z on that slice of the slice, and then there's an end, a top value of z on that slice of that slice, and that gives me the range of values of z. Okay, so that's going to be the process. And I think it's nice to see sort of a blown up generalized kind of geometric example of what do these bounds mean, what do they look like, what variables are playing what role at what stages, right? Going forward from here, we're just going to see a bunch of examples. I think that's really the best way to get a working experience, working feel for how triple integrals works and how the bounds on triple iterated integrals is just dive on in, and we're going to get our hands dirty and do some. Okay. How are we doing so far? Anybody have any questions so far? Okay. A little bit of terminology first before we go on. How we refer to these three different single variable integrals. And again, there's this awkwardness. You can't say first, second, third, right? Because in the slicing process, this integral is the first in the slicing process, right? But when it comes to actually cranking out the integrals, well, that one is the one where you're actually going to be doing the integral first. So awkward in terms of how do you refer to them. So I like to stick with the pattern that we have from previously, and that is we talk about the outside integral and we talk about the inside integral. Those I think are pretty natural, self-descriptive, right? It's just exactly what it looks like it ought to mean, right? But that does leave the question of what do we call this one? And you can call it the middle integral, but great convenience, you could also call it second, right? Because it's second whichever way you're thinking about it. And so that's kind of every so often you get lucky, right? So either of those, middle or second, to refer to that one. Okay. All right, but first and third as terminology just doesn't really make any sense. Okay, let's get our hands dirty. Here we go. Here's an example of a domain. Suppose you're interested in this solid region here that's bounded by these four planes. The plane x equals 0, y equals 0, z equals 0, and then here's a fourth plane, x plus y plus z equals 1. Let's try to draw this. Now I'm going to have to zoom out for space. So here it is, one at a time, the plane x equals 0. There's the plane x equals 0. Right, etc. Y equals 0. Etc., etc., etc. Okay, I appeal to your geometric experience, intuition, ability to visualize. What you get when you use all four of these planes is you get this tetrahedron. Now that's a little bit of a geometric challenge there, right? And by the way, there's no way around this. There is no sort of like, I want to do this algebraically. Sorry. You got to think about this geometrically. I mean, I suppose technically you kind of could in a way, but doing this in an algebraic manner without drawing a picture, without seeing it geometrically, it's unthinkably inconvenient. It's clearly inferior way to do this problem. This is we're getting into the part of the course where geometry and thinking about things geometrically is unavoidable. It's going to have to be part of your solution, part of your way of doing this stuff. This class is intrinsically geometric material. A little bit of language I do need to talk about. This word bounded by means two things. We talked about this when we were talking about two-dimensional regions. It means that the surfaces that I'm about to list are part of the boundary of our region, but it also means that the solid itself is in fact bounded. Right? So this is another thing you kind of got to think about. There are other three-dimensional regions whose boundaries are made up of those four surfaces. Right? And again, you can think about that. For example, if I look at the part of the first octant that's sort of, if you will, on this side of that plane. Right? Well, its boundary consists of four pieces that are, each one of which corresponds to one of those surfaces. Right? But the part of the first octant on this side of that plane is simply not bounded. Right? So make sure to be careful about how you interpret. It's part of the problem is that you have to make a proper interpretation of what solid actually is bounded by these planes. Okay. All right. So all that said, now let's see. Can I do this here real quick? Yeah. Okay. So looking at this solid, I'm going to do my slicing in the order that we talked about on the previous page. Not that it matters. You can kind of do the slicing in any order you like. We'll talk about the options on that as we go along. But if I were to do my x slicing first, a slice perpendicular to the x-axis, you might say a slice corresponding to a fixed value of x is a slice perpendicular to the x-axis. It's a plane like that. The slice looks like this. Whoops, I missed. The slice looks like this. Right? That's what an x slice of that tetrahedron looks like. And I appeal to your geometric intuition. Those slices go from there to there. Right? There is a first slice back there. And the slices proceed, and as x increases, they get sort of smaller and smaller, and then your last slice is, well, it's this sad little single point slice right there. Right? So you might say your bounds on x are determined by that point and that point. Everybody on board? Okay. Okay, now we'll get to the algebra in a second, but looking at a given fixed value of x. Now, the rest of our attention on this problem, we're going to be constrained to that x slice. So, on that x slice, what do our y slices look like? Well, a y slice for a given value of y, right? We're looking at a slice perpendicular to the y-axis. What happens when you take this x slice and slice it perpendicular to the y-axis? Well, again, you get a little segment like that, right? And so, all right, well then, where do the y slices start? Where do they end? Again, geometric appeal. The first y slice on this x slice is going to sort of happen there, if you will. There's going to be a y coordinate there, and then the last slice. These slices on the x slice sort of end there, if you will, corresponding to a y coordinate there. Okay. All right, so now, having made a mess, let me clean it up a little bit. For this value of x, for this value of y, choosing, in other words, an x in the x range, a y in the y range. Note that the y slice of the x slice looks like that, and on that y slice of that x slice, we have to ask the third question: what's the range of values of z? Well, there's the lowest value of z. That point has the lowest value of z, right? And then that point has the highest value of z. And we can talk about finding these z coordinates. Everybody see how the slicing is going to work? Okay, let's talk algebra now How do I find these points? Going back to the x slices, this first value of x. That point describing this first x slice, that point's an easy one. I can see it right from the picture. That's the origin. I know the x coordinate at the origin. I don't have to play any algebraic games. Sometimes things are clear, right? So the x coordinate at that point, no problem. X equals 0. Our x1 bound then, clearly 0, no problem. Let's talk about the more non-trivial question of where is that point, right? I need to know the x bound there. What is that x2? What is the x coordinate of that point? There's a process. It is shockingly similar to the process for double integrals. And that is bounds, we've already discussed, are described by points. Points are on various geometric objects, surfaces in this case, because we're three-dimensional. Those surfaces have various algebra that we can write down, equations. And then within that algebra, within those equations that you write down that describe the point in question, solve for what you want. We want an x bound, so we're going to solve for x. Okay, so that's going to be the process. Now I do need to zoom back out here at this point. Yeah, we're talking about this point here. What can I say about that point? That point's on various geometric objects. And by the way, it's going to come from the picture. So here's another situation where the picture matters. You got to do this geometrically. It's really, really, really intractable, I'm going to say, to take a purely algebraic approach to this. There are algebraic cheats that will get you right answers often. Surprisingly often, like as in maybe more than half the time. Right? But that's not acceptable. Right? And again, let me remind you, I can't emphasize this enough. I've said it before, I'll say it again. It's not a class about answers, it's a class about legitimate mathematical reasoning. So if your argument for why the bounds are what you say they are, and you happen to be correct in the answer, if your argument simply does not follow, and in other words, you got lucky, it doesn't matter that you happen to be right. Okay, so let's think it through geometrically. What's this thing on? Well, I missed. It's on that plane that has that equation. I can see it from the picture. Thank you, picture. Couldn't have done it without the picture. Okay. Well, now geometrically, what else is this thing on? Well, check it out. It's on that plane. This one here. That equation. But those two planes, aka those two equations, that still does not uniquely describe this point. There's a bunch of points that are on those two planes, right? So I need more information, and the critical third piece of information is missed again with the this plane here, right? That plane, that equation. The point we're looking for is on that plane as well, right? So there you go. There's whoops, I didn't mean to do that. I just wanted to isolate. We have the bound is described by a certain point that I can see in the picture. The point is on various geometric objects, in this case planes, that I can see in the picture. Those planes all have certain equations that I can write down. And now, as we described, solve for what you want. We're looking for the x bound here, right? So we solve for x in this equation. It ends up being pretty easy to do. After all, looking at the algebra, if y and z are both 0, that makes that third equation pretty easy. And so solve for x. It's already solved for, as it turns out, and it's 1. So this is that upper bound for the x integral. How are we doing? Is everybody on board? Okay. Does everybody see the process is actually morally identical to the one for double integrals? It's just, really the big differences are, well, now they're surfaces instead of curves. And there's 3 of them instead of 2 of them. Right? But other than that, same process. Okay, so moving along, let's talk about the, and let's see it in our integral down here, by the way, our x bounds, 0 to 1. Again, the 0 was sort of obvious, and the 1 is what we just figured out. Okay, moving on to the y integral. Let's talk about the y bounds. What are these y bounds? Well, again, every so often you get lucky. Right, those are the 2 points. Right, y, the lower bound for y is described by that point. The upper bound for y is described by that point. Within that x slice, I guess I should draw that here as well. Within that x slice, you can see the points that tell you where y starts and where y ends. So what do I know about these points? Well, again, every so often you get lucky. It's super easy. And this one is perfectly obvious what the y coordinate is. Y is obviously 0 at that lower bound. After all, it's on the x-axis. No discussion really required. That's clear. The tricky one, not obvious, is this point. Right? What can I say about that point? We play the same game. We identify geometric objects. We write down the corresponding equations. So here we go. About that point, well, I know, I can see right here from the picture that it's on that plane. I can see right here in the picture that it's on that plane. And a lot of students get stumped at this point. It's got to be a third plane, but look, it's not on that plane, and it's not on that plane. So where's the? What else do I know? What else do I write down? And here's the easy thing to forget. Don't forget, we have in fact fixed x. X is chosen, so that means it's on, if you will, this x slice. And I don't know how to write down an equation for. I mean, it's just we know what x is. Sometimes in the past I've written down x equals x, which is silly, right? But it's a way of kind of, I don't know, it feels like I'm indicating I know what x is. Right? But that's the third piece of information that we have. Now, again, what are we doing? We're trying to find the y bound. So solve for y in this equation. There it is. Solving for y. Notice that I can't eliminate x. No problem. X is known. Right? I'm treating x like a constant for this part of the integral. So y is, as it should be, a function of x. Everybody on board? Okay. All right. Okay, the z bounds. Okay, so x is fixed, y is fixed, and now the z bounds. Well, there's the lowest value of z. Okay, well, look, it's clearly in the xy plane. Z is obviously 0. There, no problem. It's this upper bound point that's going to be a little tricky. How are we going to figure out what the value of z is at that point? Well, what do I know about it? Well, I know 3 things. That point, and again, thank you, picture. I couldn't do this without the picture, but I can see that upper bound for z happens on that plane. See it from the picture. Got to have the picture. And what else do I know? Well, of course, I know x and I know y. So solve for z, as was the plan all along. We want to know what z is. There's z in the algebra we've written down. We solve for z, and of course it is, as it should be, a function of x and y. Okay, so it's the same process, just kind of different details as you go along. And we've done all the slicing up, and here's our result. X goes from 0 to 1, y goes from 0 to 1 minus x, and z goes from 0 to 1 minus x minus y. Yep.
Are we allowed to rearrange the nested integrals?
I'm sorry?
Are we allowed to rearrange the nested integrals?
What you can change the order in which you choose to do your slicing, but then you've got to reslice all over again, and all of these things are going to change. Right? And so, yeah, no, it's not like, I mean, unless your domain happens to be a rectangular box parallel to the axes, right? In that single case, then yeah, you can just go whoop, and right, that's nice, right? But that is a peculiarity of rectangular boxes. Yeah. Absolutely. So, so you got to pick an order and stick with it. Yep. By the way, there are 6 different ways that you can choose to do it, and it's kind of up to you. Now, I arbitrarily on this question did it in this order for no particular reason. I guess alphabetical order or something. But there's nothing magical about that order. I think it's a very healthy exercise. I encourage you to do this. Go through this whole process again in a handful, however many, until you feel strong with it, of the remaining 5 different ways that you could slice. And you're going to get different pictures, and you're going to have different points that are on different planes, therefore have different algebra to go through and find your corresponding bounds. And what you'll find in this case is that they're all kind of equally convenient, and it doesn't really matter for this particular shape. But sometimes it does. Sometimes it will matter. Sometimes if you slice the wrong way, bad things happen. And we're going to see some examples of that coming up pretty soon. Okie dokie. Here's another one. So we're looking at the region in the first octant, right? That's bounded between this paraboloid, which is hard to draw, and this plane. Plane z equals 1. Okay, so there's our solid. By the way, that's a pretty tough draw. If you don't believe me, try it. What are we going to do about this? Right? Sure does help to have a good picture. We saw emphatically in this case that having the picture critical, right? And now we see that here, drawing the picture is going to be really hard to do. A lot of y'all might be thinking to yourselves, okay, but I'm no good at drawing pictures. What do I do? And the answer to that question is you get good at drawing pictures. It's very important. It's unavoidably important. So now here's the good news about it. It's a skill. It's something that you can learn. There's techniques. There's things to know, right? It's not just, some people just have this blessed ability to, So keep in mind, we're not asking you to draw a human face and convey a human emotion. That's not what we're talking about, right? We're talking about this very cold and simple matter of drawing geometric figures, right? So, like I say, things to know, and all discussed in my little YouTube blurb on drawing. There's 2 little videos there, and if you think you need the help, that'd be a great thing to spend a little bit of time with. And then it's going to take a certain amount of practice. And side note, this particular picture is one of the ones that I discuss in great detail. And I think it's in the second drawing video. So I'm going to spend some time on it. Make sure you get good at it. And like when I say good, I don't mean aim to be able to reproduce the figures that are in the textbook that they've done with computer generated, and like fancy shading and stuff like that. Absolutely not. Your goal is to be able to do something in the general sort of category of what I've got here. Namely, it's not published. It's not like pretty. I can't compete with Mathematica, right? In how nice it looks, but this communicates all the information that you really need. Okay. So let's talk about which way to slice. Recall in the slicing process over here, we have to solve for certain variables. Like here, look, I put z on the inside as the inside integral, and check it out. In fact, I had to solve for z in order to find the z bounds. So you gotta, just like with double integrals, think strategically. Look at the algebra that you've got in front of you and ask yourself, which variables would you rather solve for? And then slice accordingly, right? So I look at this situation here and I think, oh gosh, I sure don't want to, if I can possibly avoid it, it'd be kind of nice to not have to solve for x there, because then I get weird square roots. But solving for z, no problem. I'm happy to solve for z. I've already solved for z. I don't even get square roots if I solve for z there, right? So there's a pretty strong motivation then to put z as your inside differential. Right? So that kind of thing. So you want to think in those kind of terms. And there's also geometric arguments, with corners and stuff. But we're going to see some corner examples coming up real soon. Okay, so no particular reason. I guess just to mix it up a little bit, let's do our y slices first, right, on the outside to remove ambiguity. But and the slicing process, let's do y slices first. Here's what it looks like. There's your range of values of y. Here's, if you will, your first y slice. Here is a generic y slice, and then here's the very last y slice. Right, so you can pick some points, whichever points you like, that correspond to your first and last slice. No particular reason. I'm going to take that point because it's easy to define my first slice, and of course I don't really have much of a choice on what to choose to define my last slice, but I got to figure out what I know about those 2 points. The first one's obvious. It's the origin. I know the y coordinate. 0. Easy. Sometimes it's exactly what it looks like it is. This one here, the upper bound for y, not immediately obvious. Here we have to do some work. Notice that it is in this plane there with that equation. Now, where did I get that from? This equation, x equals 0, was not part of the statement of the question. I guess it in some way comes from the fact that we're looking at part of the first octant, right? The edge of the octant kind of defines that plane. But the important thing I'm getting at is I got it by looking at the picture, by having a decent picture, inferring geometrically from the picture that that's the plane. That's one of the planes that defines that point. Well, it's also in that plane. Thank you, picture. That one happened to be given in the statement of the question. Right? And furthermore, though, right, there's lots of points that are on both of those planes. That doesn't nail it down for me, but furthermore, it is in my paraboloid. So there's 3 equations, and between those 3 equations, I can that uniquely characterizes that point with the understanding that y is positive, right? And so you can solve for y. Now, a little bit of algebra there, right? Solve for y on that point. So make sure you can do that algebra, and there it is. And 1 is your upper bound for y. Okay. Et cetera, et cetera. Things do get a little funky. You notice that when you fix a value of y, your y slice is kind of hard to draw. And sort of the geometry of figuring out the next bounds is, so I'm just a little uncomfortable thinking about slices of weird shaped slices. So doable, right? Perfectly fine. I'm going to let you all fill in the arguments on that on your own. I want to move on, though, to a different point of view on this, which is really nice. And this is the projection point of view, or the shadow point of view. So notice, neat fact, our solid R, right, that solid has the exact same range of values of x and y as its shadow does. Right? If you just project straight down, just push everything down into the xy plane like that. Well, all you're doing when you push straight down, like, you're just changing z coordinates. You're not changing x's or y's, right? And so the range of values of x and y on the original solid that's hard to draw, well, it's the exact same as the ranges of values of x and y on the shadow. So while you're looking for the ranges of values of x and y, namely while you are doing sort of the first 2/3 of the problem, while you're finding the outside bounds and the middle bounds, there's really no need to look at the solid. Phooey on the solid. Just look at the shadow. It's a lot easier, right? You can without too much trouble find the equation of the shadow. The shadow is where, let's see here. So it's where this plane z equals 1 intersects this paraboloid, z equals x squared plus y squared. And so where they intersect, namely, where are all the actions happening down here, namely that intersection curve, okay, well, no problem. That's just, that's what you get when you set those equal to each other. And so, again, fooey on the solid, let's just look there. And much easier problem, right? It's kind of a double integral problem even. You can almost leaps off the page for you what the range of values of x and y are. So let's just do it again just for fun. So y goes from 0 to 1, and then for a given value of y, you can see that x goes from, well, there to there, and the equation of that point is easy to write down. There it is, and solve for x, right? It's just much easier. Certainly much easier picture. Much easier to slice up a two-dimensional thing than a three-dimensional thing. So be on the lookout for situations where that might be a convenient tool. It comes up sometimes, right? Not so much, really, in a case like this. Here the pictures are pretty easy. I don't know if, you can, I suppose. But in a case like this, very convenient. Okay, fine. Let's talk about z-bounds, though. Finding the range of values of z. So for a given value of y, on that value of y, then for a given value of x, right? Looking at our x slice of our y slice there. What is the range of values of z? Well, there's going to be a starting value of z. There's an ending value of z. The ending value of z is obviously 1, right? Again, from the picture, that ending point is clearly in the plane, z equals 1, so solving for z is easy. Right, but the interesting one is that one. And play the usual game. Notice that it's on this paraboloid. How do I know it's on that paraboloid? Because I can see it in the picture. I have this geometric intuition for what happens when I take slices of slices, and what happens when if I fix a point in the shadow and look straight up, I can just see in the picture which surface it is. Right? That is that first value of z. So, take advantage of your picture. And then solve for what you need, and solving for what you need. So we're solving for z, then, in this equation that we just identified from the picture, and easy to do. And so here's your z bounds. Z goes from there to there. Everybody good? Okay. All right, so I'm going to start moving a little faster through the algebra because we've seen sort of in great gory detail careful development in a couple of cases here. I am going to suggest, by the way, here, do it in a couple of different orders. Do it that way. See what happens. And then worse, do it that way and see what happens. This is a sort of a, do it so that you can make the decision that you don't ever want to do that again example. Right? But it's still a healthy exercise. It's a good little bit of mathematical weightlifting. It'll develop all sorts of good little mathematical skills. Okay. Another example. This is a classic. Looking at the unit ball centered at the origin. It's a really hard picture to draw. Really hard. I probably spent 30 minutes on this because I knew I was going to be using it in class multiple times. Right, so I wanted to get this as good as I could, and even this leaves a lot to be desired. Right, so it's a tough geometric challenge to draw. So anyway, just be prepared for that, and keep in mind again, this is something you're going to have to face at various points. Homework exercises, exams, such. So anyway, that being said, x arbitrarily doing our x slices first. There's our x range. It starts at the back of the ball. It ends at the front of the ball. Write down the algebra. Off you go. For a given value of x, we're looking, therefore, at an x slice. On that x slice, which, again, I'm not going to leave on there. Maybe I'll just draw the boundary of it. On that x slice, what's the range of values of z arbitrarily? Let's do our z slicing. Well, z slices, come through like that, right? The Z slices will therefore end up looking like little segments like that. The first one of which is down here. The last one of which is up there. Right? And now begins a tough game. What do I know about those points? This one I am going to talk about just a little bit because there's a tricky hidden bit of information there. Those points, let's just talk about the upper one. That upper bound, I know what X is. See, where did yeah, here we go. I know what X is. I know what X is. I can see from the picture that it's on the ball. So I know that equation. The third hidden piece of information that helps me see what that upper bound for Z is from the symmetries of the ball. I can see that it's in the XZ plane and Y is equal to 0. You got to see that from the picture. You got to understand the symmetries of the ball, right? To notice that is the third piece of information that it takes to get what you need to know about that point. Okay. All right. And then algebra. Do notice, by the way, how all this works out. This is a super ugly integral. That's the resulting triple iterated integral. And recall, bounds, it's not like single variable calculus anymore. In single variable calculus, the bounds are just the numbers you plug in at the end. Who cares? Not so with double integrals. With double integrals, whatever bounds are on the inside, that becomes part of your integrand for the outside integral. Well, so these square roots are going to be part of our dz integral. And then continuing the ugliness, if I make it through that dz integral, then these square roots are going to be part of my dx integral. So this is a horrendously unattractive prospect, right? To actually crank out this iterated integral looks like no fun at all. Okay. Good news. There's a clever way around that makes this problem, I don't want to say easier, but it trades the ugliness of square roots for a different kind of ugliness that's actually a lot less ugly. And so what we are going to see, I'm going to just try to be vague, some methods that help us deal with this terrible situation. Okay, here's another one. I want y'all to see all the various kinds of challenges that you might face in these sorts of problems. Suppose your domain, right, described by various surfaces that it's bounded by. Suppose it's bounded by these 5 planes. There's 2 really tricky bits about this question. One is, what in the world do I do if I am given 5 planes like this? How in the world am I supposed to actually draw what this is? Right? And so it's hard. What I'm not expecting you to do is to literally just draw all 5 planes and then just kind of, I see how these things intersect, right? That really would be very, very hard. What you can do, though, is every so often notice convenient little tricks. Notice, in particular, no y's in these equations here. No y's. That means that all 3 of these planes are parallel to the y-axis. So, z equals 0, z equals x, z equals x, and x plus z equals 2, you can see this triangle right here, and knowing that all of these planes are all parallel to the y-axis, you can just drag this whole picture parallel to the y-axis and see that what we're talking about is part of a prism. So you make that observation first, and then having done that, it's no big deal to notice that, well, y equals 0 is this back end over here. And then the last one, I had a little bit of an artistic challenge, but y plus z equals 3. You got to kind of think about what that plane looks like. Think about how that slices through. It kind of cuts through. We've got this prism here, and that plane kind of cuts through at an angle. All right, so we have an angled slice on that prism, thus giving you this face. here. So there's a bunch of details to follow through on this, but having seen the picture, let me just point to the strategy. If you think about all the different ways that you can slice, and these are just planes, the algebra is going to be easy on this, right? You're solving for various different variables, no big deal. The tricky part of this problem at this point is figuring out which order to do your slicing. And notice some bad things happen. If you do your x slicing first, then your cross sections that look like that will eventually, you will cross through that edge, aka corner. And remember what we talked about, we don't like to slice through corners. Roughly speaking, the problem then is that the upper bound, later on down the road, this upper bound for z, that comes from that face for the first few values of x, well, it will eventually come from this face for later values of x. So same punchline, don't slice through corners. Right? So you can see if you do your x slicing first, you're going to slice through a corner there. So don't do your x slicing on the outside. Likewise, don't do your y slicing on the outside. Look at the nightmare that happens if you do your y slicing on the outside. Your y slices look like this, which is all fine and dandy, it seems, until eventually you slice through that corner, and then your y slices change very dramatically. They're not even qualitatively the same, right? They're not even triangles anymore. Right? So you slice through a corner. Don't do that. Right? So on this question, there's really only one sort of option for the slicing to do on the outside, and that is do your z slicing first. And notice your initial z slice is a little rectangle, and then your subsequent z slices are rectangles, and they just continue to be rectangles, and everybody's happy. And the very last one is, somewhere, but who cares? We're done. So you got to look at the picture and think about order. Now, real quick. Oh no, I'm 3 minutes over. I'm sorry. Okay, so I'll have one last comment about this question, about this example next time. See y'all later. Have a good one. Yeah.